Assalamualaikum. My name is Nazraiman bin Nizar. I'm from class DKA4A and my matric card number is 11 DKA 19F1017. And this is experiment virtual lab about tensile test on mind steel. So for the theory, in tension test end of a piece are fixed into grip connected to a straining device and to a load measuring device. The test involves straining a test piece by tensile force generally to fracture for the purpose of determining one or more of the mechanical properties. The straining unit of universal testing machine consists of main hydraulic cylinder with robust base inside and piston which move up and down. A lower table connected to main piston through a ball and ball seat is joined to ensure axial load. There is a connection between lower table and upper head assembly that move up and down with main piston. The control panel consists of the power pack complete with the drive motor and an oil tank, control valve and autographic recorder. Load indicator system consists of a large dial and pointer. A dummy pointer is provided to record the maximum load reached during the test. Load is applied by a hydrostatically lubricant ram. Main cylinder measure is transmitted to the cylinder of the pendulum dynamometer system housed in the control panel. The cylinder of the dynamometer is also of self-lubricant design. The load transmitted to the cylinder of the dynamometer is transferred through a lever system to a pendulum. This displacement of the pendulum actuates the rack and pinion mechanism which operate the load indicator, pointer and autographic recorder. The deflection of the pendulum represents the absolute load applied on the test specimen. Return movement of the pendulum is effectively damped to absorb energy in the event of sudden breakage of a specimen. Test strain graph of mild steel. So this is the graph. Ultimate stress, fracture stress, yield stress, proportionality limit. The stress strain graph of mild steel is divided into 4 areas, in which each first section represents elastic deformation, and in remaining area only plastic deformation will take place. However, the material behaves differently in each individual phase of plastic deformation. Area B defines a flow region. Here the material is stretched beyond its elastic loadability, and within the flow region the stress change very irregularly with increased strain, so that the wavy line result in the graph. In section C, the stress increase sharply and the plastic deformation also increase. The maximum loadability, the material cross section begin to reduce in size and ultimately failure occur. Increase sharply and plastic deformation also increase. At the maximum loadability, the material cross section begin to reduce in size and ultimately fail occur. Elastic deformation. A. The first phase of the stress training, the first stress strain damage is elastic deformation. When the stress acting on the material is removed, the material regains its original length. This is called complete recovery or resilience. Again, the area of elastic deformation is divided into phases. In the first phase, the material stretches proportionally to the stress acting on it. The extension is also called linear elastic or proportional deformation. The point at which the linear elastic elongation is maximum is called the proportion limit. Beyond this limit, elastic deformation still takes place. However, greater elongation occurs in this section under increasing applied force. Therefore, the elongation or straining is greater than the increasing stress. The flow region B. Further small increase in stress can be enough to cause the proportional limit to be exceeded. The highest flow point is the point accompanied by the initial sudden loss of quality. As a result, the stress required to continue the elongate the material reduce immediately and reach the lowest flow point. After this point are exceeded, even if the force are removed immediately, the material does not regain its original properties. When the stress is increased again and the dislocation start to wander, an increase which leads to further quality total loss at the first flow point. Stress and strain behave irregularly in relation to each other. Material hardening. C. If the stress is increased further, an increased number of upright dislocation from in the crystal lattice prevent the movement of the previous still sliding dislocation. At the same time, the stress is in the crystal lattice continue to increase, which cause hardening of the material. Here, the metal becomes stronger as the strain increase. Hence, it is called as strain hardening. However, its process cannot be continued infinitely. Each material has its specific maximum force. Necking. D. If the maximum force is exceeding, the material begin to neck in the crystal lattice of the metal bar. So many dislocations have occurred that they can no longer lead to the hardening, but instead contribute to the formation of void or cavities. A part of necking, the void also cause the material cross-section to reduce. The stress now acts on an increasingly smaller cross-section, which enhance the process still further. As the tensile test continue, the necking increase until the tape cross-section can no longer withstand the stress. This is when the metal bar tears at the weakest point. Finally, the specimen will have increased in the length and reduce the cross-section area. Percentage elongation. Increase the gauge length of the test piece at maximum force, expressed as a percentage of the original gauge length, Li. The value of percentage elongation depends on the gauge length chosen according to the BIS specification. A gauge length of 5.65 square AI 5D rod is to be used. Percent elongation equal LF minus Ly divide Li multiply 100, where Li equal initial length and LF is final length. Percentage reduce in area, maximum change in cross-sectional area that has occurred at the neck during the test expressed as a percentage of the original cross-section area. So the percentage reduction in area equal to AI minus AF divide AI multiply 100, where AI equal initial length, AF equal final length, tensile stress corresponding to the maximum force, tensile stress, ultimate load divide AI multiply MPa. Yield strength, when the metallic material exhibit a yield phenomenon, a point is reached during the test at plastic deformation occur without any increase the force. Yield stress, yield load divide AI equal MPa. Modulus elasticity is the slope of initial linear proportion of stress strain curve. Modulus of elasticity E equals slope multiply gauge length divide AI equal GPa. Stage in ductile fracture. The failure of ductile material under the tensile loading can be attributed to cup and cone fracture. The form of the ductile fracture occurs in stage that initial after necking. First, small micro void form in the interior of the material. Next, deformation continue and the micro void enlarge to form crack. The crack continue to grow and it spread laterally towards the edge of the specimen. Finally, the crack propagation is rapid along a surface that make about 45-degree angle with the tensile stress axis. The new fracture surface has an irregular appearance. The final shearing of the specimen produce a cup type shape on one fraction surface and one cone type shape on adjacent fraction surface. In this central interior region has an irregular and fibrous appearance which signifies plastic deformation in material. This is the crack grow at 90 degree to apply stress, maximum shear stress at 45 degrees. This is a fibrous shear. Detailed and important information of the mechanism of fraction can be obtained from microscopic examination of fraction surface. This study is known as fractography. Variation of local elongation with position along gauge length of tensile specimen. The measured elongation from the tensile specimen depend on the gauge length of the specimen or determination of the cross section. This is because the total extension consists of two components, the uniform extension up to necking and the localized extension once necking begins. The extension of uniform extension depends on the metallurgical condition of the material and the effect of the specimen size and shape on the development of neck. The shorter the gauge length, greater is the percentage elongation. Procedure. Objective: to study the mechanical properties of mild steel specimen under tension load. Step 1. click on the tensile test on my steel file. A window will open as shown. So the objective to study the mechanical properties specimen under the load apparatus use universal testing machine, dial indicators, scale and vernier caliper. So step 2, click on the next button to move to the next step. So step 3, to measure the diameter of the specimen using vernier caliper, click on the caliper knob to adjust to the diameter. So step 1, measure the initial diameter of the tension test sample in two perpendicular direction using vernier caliper and calculate the initial area. 4, click on the measuring scale to measuring the length of the specimen between the grid. Step 2, measure the length of the specimen between the grid using a scale. Length of the specimen between the grid equal to 100 millimeter, and then we click this to next step. 5, click on the hammer to make a punch mark at the distance of 2.5D, then click next button. 6, click on the rotating lever to lower the machine bottom part. Drag the specimen and place it on the position when the arrow is pointing. Then again click on the rotating lever to adjust the height, and then the dial gauge is mounted. 7, reading on the dial of the extensometer are adjusted to 0 by clicking on adjusting knob of extensometer. 8, click on green button to switch on the machine. The extensometer reading variation with load is observed and can be downloaded via download data. Here the stress strain graph of test is shown. Click on the view data to view the data. 10, click on view data or view slope to view test data or the slope drawn to the plot. 11, click on join the piece of the specimen to join it to measure the change in diameter. 12, join the two specimens to measure the change in the specimen length. And the last 13, input the calculate result and then click on the check to view the actual result. So this is a test your knowledge. What is the question 1? What is the distance between the punch mark in the experiment? 2.5 diameter. Next, arrange the orders. Okay. Yep, point strain. By conducting the experiment, the mode of fracture observed in my steel specimen is the steel deformation of the material is associated with hardness of the material. Okay, this is a simulator tensile test on mass steel. Objective to study the mechanical properties of mass Marks the specimen under tension load. Apparatus use universal testing machine, dial indicator, extensometer, scale, and vernier caliper. Step 1. Measure the initial diameter of the tension test sample in two perpendicular direction using vernier caliper. Next, DIX equal 12.55 mm, DIY equal to 12.55 mm also. Initial diameter is D equal to 12.55 diameter. Step 2. Measure the length of the specimen between the grip using a scale. Length of the specimen between the grip equal 192 millimeters. Step 3. Punch mark are made at the mark are made at a distance of 2.5 diameter. Distance 2.5 diameter. Next, 4. Insert the specimen into the position and mount extensometer on the specimen. Drag the specimen here. Next, step 5. Reading on the initial dial A and B of the extensometer are adjusted to 0. List count of the extensometer 0.01 millimeters. Step 6. Experiment is conducted. Load extensometer readings are read at regular interval of load up to the yield point. Ivory scale reading are noted till the specimen failure. Press the green button to start. And the data will be downloaded. And press red button to stop download data. And next, this graph view data. This is the data. This is load versus extensometer reading. View slope. Step 9. Join two pieces of the test sample and measure the diameter at the neck of the specimen. Final diameter 7.475 millimeters. Next, step 10. Measure the final length between the three punch marks. Final length between the punch mark equal 86 millimeters. Okay, step 11, observation and calculation. Here stress y per millimeter square. So the answer is 207.3. The tensile strength is 461.02. The modulus of elasticity 211.48. The percentage elongation is 38.04, and percentage reduction in area is 64.553. Check. Okay.